Hello students and welcome back to Study Room. So till now we have studied about resistors, resistivity, and we have studied what are the factors that affect the resistance of a conductor or a wire, right? So now we are going to study how resistors or how wires can be connected to each other. There are two ways that we're mainly going to study of how they can be connected to each other, and that is what we're going to do next in this chapter. Okay? So, this slide says, have you ever thought about how many possible ways we can connect the components of a circuit? Well, that is what we're going to study about. Okay? Great. So, types of circuit connection. So, there are basically the two broad types that we are going to study about are parallel circuit and series circuit. Okay. Now, what is the difference that you can see in the parallel series circuit here? This X and a circle here is basically what? It's represented like this. What is it? Can you see in the figure what exactly that X means? It is nothing but the light bulb, right? So here, how can you see these two light bulb connections? Are they different in any way? Do they look the same to you? Do they look different to you? If they look same, why do they look same? If they look different, why do they look different? Okay, so right now I'm not going to answer that question for you. I'm going to teach you and then that question would be answered automatically. Okay, but right now you just need to look at these two figures and just think what can you see is the difference between the parallel and the series connection. One thing which I think is the major difference you can see is in series circuit they're somewhat like side by side, but in parallel circuit they're like one on top of the other, or one is upwards and one is downwards, right? That's the main difference that you can see in the connection of the light bulbs. This light bulb can actually be replaced by a resistor also. Like in place of this symbol, it can be this symbol, the resistor symbol also. That doesn't make a difference. It's just to tell you what it actually looks like, what those two different kind of connections, the way the components are connected looks like. Okay, so these are the two ways, series and parallel. Okay. Now, what exactly is resistors connected in series? So, as your PPT says that when components are connected end to end, what does that mean? Look, this resistor 1 has ends. I'm just going to draw this same diagram explaining it to you right here. Okay, so this resistor is resistor 1 or R1. It has starting point as A, ending point as B. Now this resistor R2, it has starting point as B and ending point as say C, this R2. The resistor R2 is connected between points B and C. So it's connected between points B and C, and similarly the resistor R3 is connected between points C and D. Say this is how they are connected. Okay, there are three resistors R1, R2, R3. Now look at this. The ending point of R1, the resistor R1 is actually the starting point of R2, right? The ending point of R1 is B and the starting point of R2 is also B. So what does this mean? That they are connected end to end. Like it's written here, they are connected end to end. That is what we mean when we say that they are connected end to end. That one end of one resistor is connected to another end. Well, you can say that B is not the end of R2, it's the starting of R2. But by ends, I mean the 2 points between they lie. Say AB or CD. So this C or D, even if C is coming first, we call these the two ends of the resistor. Okay, end doesn't mean the point that is coming at the ending. That's not what I mean here. So by ends, I mean the 2 points at the two ends of the resistor, the left and right point. They're both called ends. So basically they're connected end to end. That means that where one resistor ends, the other one starts. So that is called the series combination of resistors. Okay, when the resistors are connected end to end. Okay, now what is the next thing that we want to think about? We want to think about that if we change the position of the ammeter In a series connection, will the value of current change? The answer is no. The value of current does not change if the position of the ammeter is changed. Why is that? I'm just going to tell you. Just think about this. Just if the voltmeter is not here, just think about this circuit like this. This is R1. Here the second one is R2. And the third one is R3. And just think about that there is this battery. You can represent it with just one cell also, that's okay. A switch K or a key K. And if I have not connected ammeter, I'm just taking a basic circuit. So current flows from positive to negative. So the current flows like this. This is the current. Now the current, just think if you are walking on the path of the wire. Say you are here. You are walking in the direction of current. You are standing here, right here at this point. Okay, you are standing here and you are walking along this wire in this direction, in the direction of the current only. So when you go towards this direction, when you go in the direction of current like this, where will you go? Do you have like 2-3 paths to go to? Can you take this path, this path? No, right? There are no other paths. There is only just this one path for the current to go in. So the current goes through this path, and the same current is going here also, the same current is going here also, and the same current is going here also. This is important to remember and understand, because this concept is going to be used in the parallel combination also, and it would help you understand why the current doesn't go in just one direction. So did you understand what I'm trying to say? You just think as if you are walking along that path of the wire in the direction of the current. You don't have any other direction than this to go from, right? So you just have this path. So the current I that is walking from here walks like this. Like if you walk like this, you go through the first resistor, you go through the second resistor, and you come back here. So in a series, so what is the important thing that is to be noted here? This is a triple star point. This is a very important point. In series combination, I'm just writing combo, current through all resistors is same. You've understood this? Look, what is the current that is going into, look at my figure. What is the current that is going into resistor R1? It is I. And the current that exits is also I. The current that is going into R2 is I. I is the one. Why is the same current entering and exiting? Because the current doesn't have any other place to go. The resistor might be offering resistance. I'm not saying it's not. But the current will come out of the resistor as it is. It might like face some difficulty if the resistance is high, but it will still come out. So this is why anywhere you put the ammeter, you put the ammeter here. Here also the current is I. You put the ammeter somewhere here between R1 and R2. Here also the current is I. You put the ammeter at this end after R3. Here also the current is I. So that is why the current is the same at every point in a series combination. Thus, no matter where you put the ammeter, the reading will be the same. Okay. I hope this is clear now. I'll start. Okay. So now I'm going to show you another small animated GIF, which will make it more clear how the current flows, and it will make it more clear why I was saying that the current doesn't have like any other direction to flow. So it is the same through all the resistors. Okay. Okay. So in this animated video, you can see that from the voltmeter or the battery, sorry, not the voltmeter, the battery is the V that is connected. That's actually the battery. And there the potential difference is being generated. Because of the potential difference, current flows, right? So you can see that that little red dot is actually representing the current. So what is happening? The same current is going from the battery, going up, going through resistor 1, going through resistor 2, going through resistor 3, and then coming back and circling again and again. So this is what I was trying to explain to you, that the same current flows through all the resistors in a series circuit. Okay? Moving on. Now effective resistance. Now you saw that there was not just one resistor connected, right? So you remember when we applied the formula V equal to IR, there was only one resistor that we were talking about. But now we have one, not just one, we have 2, 3, sometimes 4, 5 resistors also. So then what are we going to say? Are we going to take just the resistance of R1, or are we going to take just the resistance of R2, or just the resistance of R3, or are we going to take the resistance of all the resistors combined? We are going to take all the resistances combined, right? So for that, for having or considering the resistances of all the resistors combined, we just need to know how we are supposed to add it. Like we add whole numbers, like we add 3 and 2. We just do 3 plus 2 equal to 5. We just simply add them. But this is not addition of normal numbers. Resistor additions have some rules based on how they are connected. So now we're going to learn, in case of series combination, what is the equivalent resistance. Equivalent means the total resistance of all the resistors connected in the circuit. So we're going to see how we calculate the equivalent resistance of the series combination of resistors. Okay, great. Now, before looking at all of these complex situations and all the complex equations and everything, I'm going to break it down step by step for you so that you don't have any confusion. Okay, now just think about this. This battery right here is providing some potential difference. We already know that the battery helps maintain a potential difference across the terminals, right? So because of that potential difference, what happens? The current flows, like charges flow, and thus the current flows. So a current, say I, is going out of the battery, is coming out of the battery. That same current I is flowing through each resistor. This also we have established. Now think about this. This is resistor R1, this is resistor R2, and this is resistor R3. R1, R2 and R3, right? So now if I want to write, we know that the equation for VI and R is V is equal to I into R. Now we know the R is actually R1, R2, R3. We don't know the exact value in ohms, but we know we have given the names R1, R2 and R3, right? And the value of I, we know, is just one single I for each and every resistor. So now if I want to calculate what is the V for each resistor, so say for R1 I am saying the potential difference across A and B. The two terminals of R1 is V1. So what is the formula of V? It is I into R. So V1 is equal to I, because I is the same, into R1. Here the potential difference between BC is V2, because it's for resistor 2. Now the concept that you have to keep in mind here is the potential differences across 2 points, right? So we are calculating the potential difference across each of the 2 ends of the resistors. Okay. Now V2 is V equal to IR is the formula. What is the current? What is the current that is flowing through it? There is no I1, I2, I3. If there were different currents flowing through each, then we would have had to give them different names. We would have had to call them V1, I1, I2, I3, like that. But we saw, because the current has only one part to go, so it's the same, which is I. So V2 is equal to I into, what is the resistance here? R1, R3, what is it? It is R2. Similarly, V3, which is the potential difference across CD, is equal to I, which is the common current, into R3. Right? Now, you remember the battery. Come back to this given diagram here. This battery has some potential difference that it causes, right? It maintains a potential difference. Now, what do you think? Can these potential differences, the V1, V2 and V3, if we take them all together, shouldn't they be equal to the source potential difference? Think about this. Like someone has, say, 9 toffees and it has to be distributed among 3 people, right? So no matter which way it is distributed, even if the first one has 1 toffee, the second one has 4 toffees, so 4 plus 1, 5. How many toffees are left? 4 toffees are left, right? So if the last person has 4 toffees, that means 1, 5 and 4. Even though the 3 different people had 3 different number of toffees, but all combined they become the initial number of toffees that we had, that is 1 plus 5. Sorry, did I say 1 plus 5? That means if it's 1 plus 4, then it's 5 toffees. So if the first one has 1 toffee, the second one has 4 toffees, that means 5 and 4 is left. So 1, 5, 4. If that is the number of toffees, so combined, basically what I mean to say is that no matter how the toffees are distributed, all of them when they're added up, they have to be equal to the initial number of toffees, that is 9 toffees, right? Similarly, if the battery is like the parent, right? And the battery that is the parent is distributing the potential difference across, the potential difference, the battery that is the parent is causing the potential difference in the whole circuit, right? But these these 3 resistors, which are like the babies of the mother battery, that the parent battery, those resistances basically divide that potential difference among themselves, right? So, don't you think all of these individual potential differences added up should be equal to the initial potential difference that the battery is providing? Makes sense, right? The initial, say it's one big potential difference, say V. And this V is divided in any way. It doesn't have to be divided equally. It is divided between the 3 resistors, V1, V2 and V3. These are the 3 potential differences on the across the 3 resistors. So the sum of these potential differences should be equal to the parent potential difference, which is capital V that we are saying. So this is the concept that we are going to be using. So we have here broken down V1, V2 and V3 using Ohm's law, V equal to IR, and using the concept that I is constant in all, and obviously the resistances are R1, R2 and R3. Now we say that the potential difference of battery is the sum of individual potential differences across resistors. Because where is the potential difference coming from? How is there a potential difference across the resistors? Because the battery is providing and maintaining a potential difference, right? And that potential difference, which is say 10 volt, 20 volt, whatever it is, we're just calling it capital V. That potential difference is what is distributed among the 3 resistors. So basically what we do is this V, the capital V, which is the total potential difference of the battery, is V1 plus V2 plus V3. Like I said, if there are 10 toffees, and it is, this mother has 10 toffees, right? This mother has 10 toffees and she distributes it among her 3 children. She gives the first one 1 toffee. She gives the second one, say 5 toffees. So 5 plus 1, 6 toffees. So how many are left? 4. So the last child gets 4 toffees. Now, even though they didn't get equal number of toffees, but when you add them up, 5 plus 1 plus 4, it is equal to 10. Which means the individual toffees that they have summed up should be equal to the actual number of toffees initially. Similarly, the individual potential differences summed up should be equal to the original potential difference that is being provided by the mother, which is here in case of a circuit, the battery. Okay. Now, when we put the values of V1 and V2 and V3 from here, when we have calculated it, so it becomes V equal to IR1 plus IR2 plus IR3. Just broken it down. So here can we take I common from all these terms because I is same. So IR1 plus R2 plus R3. Then if we take this I to the left hand side, what does it become? It becomes V by I is equal to R1 plus R2 plus R3. Now think about this. If R1, R2, R3 are the individual resistances and V is the total voltage that is flowing, that is across the circuit, and I is the total current. So if V by I is the resistance of a resistor, what does total voltage of the circuit upon total current give you? The total resistance, right? So how do we say total resistance or equivalent resistance? We say are equivalent. So this V by I, this V is the total resistance. this V is the total potential difference in the circuit, which is the potential difference of the battery, and this I is the total current that is flowing through the circuit, which is also the current flowing through the resistors, but that is the total current in the circuit also, right? So V by I gives you R. So total V upon total I gives you total R, which is R equivalent is equal to R1 plus R2 plus R3. So that is how you get this formula that is written in green here. This RS means R of the S means in series. That R when the resistors are connected in series is equal to R1 plus R2 plus R3. So now even if you tend to forget what the formula actually was, you can derive it because now I have told you the logic behind it. Okay. So just look at the logic that we did. We calculate the potential difference across each. Then we know that the parent potential difference has to be the sum of these. And then we sum it up, take I common, take I to the denominator, and that becomes the total resistance. Okay, I hope that is clear now. Let's move on. Now in this example, it says an electric lamp whose resistance is 20 ohm and a conductor of 4 ohm resistance are connected to a 6 volt battery. Calculate the total resistance. So this example has a few parts to it. Okay, so part A says that we have to calculate the total resistance of the circuit. So what all do we have? This electric lamp. This electric lamp, actually there is no resistance written on it, so we would have to simplify this circuit. So this electric lamp in the question, it's given this lamp has a resistance of 20 ohm. So we can replace this bulb and just put a 20 ohm resistor in its place, right? Because we only have to find the equivalent resistance. So we don't need this lamp and all, we just need the actual resistance. So this 4 ohm is there. This is the 4 ohm resistor. Then in place of the lamp, there is a 20 ohm resistor and they're connected in series, right? So the end to end meet, that is the series. Now these two are connected to a 6 volt battery. So this is your 6 volt battery and you can put a key also. I know there is an ammeter and everything also, but you may or may not draw it because in this part we are only calculating the total resistance. You can draw it also, there is no problem in it. So this is a 6 volt battery, right? Now what did we study? That the total resistance, that means RS, or you can say R equivalent, whatever. So I'll just use RS because it means R series. That means total resistance of the resistors connected in series. That's why the S in subscript. What was it? So here first we write the given things. So we write given R1 is equal to 4 ohm. R2 is equal to, you can write the whole sentences. First given resistor 4 ohms, electric lamp, resistance of electric lamp is equal to 20 ohm. And then you will write they are connected in series. Then you will write a line that we know that the equivalent resistance of resistors connected in series is given by RS is equal to R1 plus R2. If there were 3 resistors, there would be plus R3 also. So this formula we are using, and we know here the two resistances are 2, 4 and they are 4 and 20. So RS is equal to 4 plus 20 is equal to 24 ohm. So this is the equivalent resistance in the circuit. Okay. Now let's look at the next part. The next part says, and it is the same question. The next part says that calculate the current through the circuit. Okay, great. Now we will draw the simplified circuit. Even though we know that there is the 4 ohm and 20 ohm individually, we will draw the simplified circuit because we know that the total resistance. So does it make a difference that the 4 ohm and 20 ohm are connected in series? And if I apply the series combination, I know, and I combine them and make 124 ohm resistor, does it make a difference? Absolutely not. I've just reduced my work. I had to work with 2 resistors. Now I only have to work with 1 resistor, that is the equivalent resistor. So that is what is the importance of doing this series and parallel combination. We can work with 20 resistors also, but it is going to make our work so much more harder. Right now you are using just 2 resistors, 3 resistors, you are doing it on paper. But in real life, you have to use like hundreds of resistors. So it is very difficult to deal with each and every resistor, and it's much easier when we have all the resistors combined into one resistance. So we can do our calculations efficiently. So now that I know that there is a 24 ohm of resistance, I would not write the 20 and 4 ohm differently. I'll just write one resistor as 24 ohm. Okay. Now, because we have to calculate current, you can draw an ammeter here. Now, as you should remember, it doesn't matter if the circuit shows the ammeter is here. Even if I connect the ammeter here, we know in a series circuit, the current everywhere is the same. So you can draw the ammeter anywhere. So now here I have my battery, plus minus, it is 6 volts. It is a battery of 6 volts. We complete the circuit. You may or may not draw the key, it's optional. Now, what do we use? We know that again we write the given things, or what we have actually calculated in this case. We know that the voltage is actually, voltage or V is nothing but 6 volts, the battery. Then we know that the total resistance or the equivalent resistance is 24 ohm. This is R, right? This is R, and we have to calculate the current. Simple formula, Ohm's law, V equal to IR. So here I is equal to V by R, which is equal to, V is 6 volts upon the resistance, which is 24 ohm. So 6 ones are 6, 6 twos are 12, 6 threes are 18, 6 fours are 24. So 1 upon 4, which is equal to 0.25 amperes. Okay. So that is how you calculate the current in the circuit. Next part says that calculate the potential difference across the electric lamp and the conductor. So now for this, because the question has specifically said that you have to calculate the potential difference across each and every one, electric lamp separately and the conductor separately. So this time I can't draw one resistance, that is one equivalent resistance, because that equivalent resistance is a like combined form of the electric lamp and conductor. I won't be able to tell if what is the electric resistance, what is the voltage drop across the electric lamp and what is the potential difference across the conductor separately, because they are combined into one. So for this part, I am going to draw both the conductors separately. Okay. So this is my 4 ohm conductor. This is my 20 ohm. This is my 20 ohm lamp. Here I have my battery, which is 6 volts, and my circuit is connected like this, right? So now I have to potential difference I have to calculate across AB and BC, right? So we first write, I am going to start from here, okay? Potential difference, first it's asked across the electric lamp, which is the 20 ohm one. The electric lamp is 20 ohm, potential difference across electric lamp. First we do this. Now, what is the potential difference? V. Now, if this is given R1 and this is, I am calling this R2. So, we have to calculate the potential difference across R2 first. I am calculating this first. So, we know that in case of series resistances, the V is different because the V is basically divided. What is the potential difference? It is basically the difference in potential between the 2 points. So, since the 2 points for each resistor is different, like resistor 1 is connected across AB, resistor 2 is connected across BC. So, there are different points that they are connected across. That's why their potential difference is different for each resistor. So, V2, which is the potential difference across resistor 2, that is the electric lamp, is nothing but I. Would I write I1 or would I just write I? I would just write I, because in series the current is the same, because the current only has one path to go from. So it's the same for all resistors. So it's I into R2, because we are calculating against R2 for R2. So V2 is equal to, now this I value we are going to use from the last part that we solved. Do you remember? It was 0.25 amperes, right? So we put this here, and then what is the value of R2? The value of R2 is 20 ohm. So this 0 is used to remove the decimal and move it to here. This 0 is gone, and 25 2s are 50, and I put 1 0, so it is 5 volt. V2 is equal to 5 volt. Now you are going to understand why I said it's actually the addition of all the voltages across the resistors in just 1 second. When we calculate the second part, which is potential difference across the 4 ohm resistor, then what happens? That is V1 is equal to IR1. So V1 is equal to I is 0.25 and R1 is nothing but 4, right? 25 4s are 100, and then we put a decimal after 2 points. So it is 1 volt. So what have you noticed? That V1 plus V2 is what? 1 volt plus 5 volt, which is 6 volt, which is what? The parent battery. So now this should make it more clear to you why I said that the individual voltages across the resistors is the all summed up is actually the potential difference of the battery or the voltage of the battery. Okay, so now you can see here also, you've seen it practically by a question also, that it is just the sum up of the parent battery. When you add up the potential difference across each resistor, this is only for series, you get the voltage of the battery. Okay. Now, the next question says, draw a schematic diagram of a circuit consisting of a battery of 3 cells of 2 volt each, a 5 ohm resistor, an 8 ohm resistor and a 12 ohm resistor and a plug key all connected in series. Okay. Now, what we have to take care about in this question is, does it say that a battery of 2 volt is connected? No, right? It is saying that the battery is made up of 3 individual cells. You remember I told you that the cell is represented by this. This is just a cell, and usually how we show when you have to show a cell, it's just 2 or 3 batteries connected together, right? And then I told you that sometimes when we do questions, do a lot of questions, we just use this one cell and it represents a whole battery. That's just how it happens sometimes. But in this question, it specifically told you that use 3 cells. That means 1 cell, 2 cells, the positive terminal of negative terminal of another cell, and a third cell, the positive terminal and a negative terminal of another cell. So we have to use a battery of 3 cells. Okay, let's go. So a schematic diagram basically means a circuit that you have seen in questions previous to this. Okay, we'll start in order of this only. Okay, so we have to first draw a battery of 3 cells. Great. So if I come here, this is my first cell, this is my second cell, and this is my third cell. Now, how many volts is this battery? It's given to you that it is 3 cells of 2 volts each, which means this cell is 2 volts, this cell is 2 volts, and this cell is 2 volts. So 2 plus 2 plus 2 total becomes 6 volts. So the battery that these 3 cells form together has a potential difference of how many volts? 6 volts. So 1, 2, 3, and then I straight away write 6 volts here. So all of this calculation has to happen in your brain. Okay. Now, next thing is given a 5 ohm resistor. Okay, I take this like this. This is resistor 1, say R1, it is 5 ohms. Then there is another resistor R2 which is given as 5 ohm, we have taken down 8 ohm. Another resistor is there R3 which is given as 12 ohm. And it's saying and a plug key, that means a key which is represented like this. All connected in series. There it is. That's our schematic diagram. The thing you had to take care here was not to draw just one cell and name it 2 volt. It says 3 cells of 2 volt each. That means one cell 2 volt plus another cell 2 volt plus another cell 2 volt. So it makes 6 volts. Okay. Great. Moving on. So it says, redraw the circuit of question 1, putting an ammeter to measure the current through the resistors and a voltmeter to measure the potential difference across the 12 ohm resistor. What would be the readings in the ammeter and voltmeter? So it means in question, the question that we did just now, this question that we drew. So we'll just draw the circuit again. What was it? R1 was 5 ohm. R2 was 8 ohm. Am I right? R2 was 8 ohm and R3 was 12 ohm. Okay. So, great. Connected to the 3-cell battery and then to a key. Now, what is said is, put an ammeter to measure the current through the resistors. So, ammeter, should I put it here, here, here? Does it make a difference? Absolutely not. So, say I am connecting my ammeter here. This is my ammeter. The positive of the ammeter is connected to the positive of the battery, negative to the other side. It's very important to mark the terminals of the ammeter also. Okay, and a voltmeter to measure the potential difference across the 12 volt resistor. Okay, so voltmeter we only have to put across one resistor, so we put it like this. This is how we draw a voltmeter. Positive to the positive end of the battery and negative here. Okay, what would be the readings in the ammeter and voltmeter? Awesome. So what do we do? First of all, to calculate what is the ammeter reading, what do we need? The current in the circuit. Obviously, that's what we need. And here, if we know the total voltage, we know it is 6 volts. We did it in the last question, right? 2 into 3. So it is 6 volts. We know we can calculate the total resistance, which is RS, that is the series equivalent resistance of these 3 resistors, R1, R2 and R3, right? And then we can find out the current finally. So what do we do first? We calculate the series equivalent resistance. So RS is nothing but simply R1 plus R2 plus R3, right? Equal to, what is R1? 5 ohm plus what is R2? 8 ohm plus what is R3? 12 ohm. So 12 plus 8 is 20 plus 5 is 25 ohm. So the series equivalent resistance is 25 ohm. Now we know V equal to IR by Ohm's law. So here we have to find I. So we send R here. So V is 6 upon R is 25. Right? So this is our current. So when you divide 6 by 25, you just do normal long division. You do that by yourself. I comes out to be 0.24 amperes. Okay. Then the second thing that we have to find is what would be the reading in this voltmeter. Now, what does the voltmeter measure? It measures the potential difference across the terminals. So again, V is equal to I into R. This time we want to find V1. No, sorry. Which resistor is it? It's V3. So why did we use V here? We used capital V here, not V1, V2 or V3 because it was the total resistance that we were considering. And total resistance, because we had to find the equivalent resistance, that is why we were considering the total voltage, that is the voltage of the battery and the total current that was flowing in the circuit. But now we have to find the voltage across just one component. So that's why we're going to write V1. So it is a third resistor. So V3 is I into R3. Right? We need to find V3. We know I is 0.24. And what is R3? Our R3 is 12 ohm. Right? So when we do 24 into 12, it comes out to be 288. We put a decimal here, 2 places. So the reading of the voltmeter will be 282.88 volts. Great. We've solved this question also.